Hi, so before we go into the functions of this library, I'm just going to go over what SIMD actually is. So if you are not familiar with it, basically SIMD is like CPU optimizations where instead of having to do one operations to modify a value, you can do one operation to modify multiple values. So for example, you can do additive operations to modify 8 values at a time or 16 values at a time. It all depends on the CPU architecture. So basically this plugin kind of helps with that. It has checks to see which CPU architectures you are running this code on, and then it's going to pick that. And if you don't have any optimization, it's going to do a fallback basically. So that's kind of the general idea. We kind of speed up stuff by doing one operations with more data basically. So yeah, this is the main map that you can find in the plugin folder. And it just holds few checks and tests so you can basically see what each function does and how it's doing it. So you can find all that setup inside of the level blueprint. And there is like a bunch of stuff in here, so you see kind of how I set it up. So in general, it's pretty simple, but I still felt like it would be nice just to have a quick test for everything. Also, you have this SIMD test if you want to check this, but it just like runs all of them, and it was just like a quick test I was doing while I was making the plugin. So you can kind of run this just all at once, and I can show that later. But for now, we're just gonna see kind of what operations and stuff we have. Because SIMD optimizations cannot be done on everything, it's going to be pretty specialized, so it might not be for you or for your use case, but if it is, it should help you a lot, where you can get magnitudes of performance increase just by not doing it the normal way. So in here, let's first go through classic and see what happens. So basically what we did is we added a vector, so xyz floats to an array of vectors, and that array had 200,000 items, and it took us about 300 milliseconds. You can kind of check the times and see, so it took us about 1/3 of a second. And then if we do the SIMD operation, we can see it took us probably, I kind of know already how much, but it took us about 20 microseconds. So just for the scale there, 300 milliseconds versus 20 microseconds, and you have 1000 microseconds in 1 millisecond. So that's like, I don't even know, like 10,000 times more expensive doing it just like a normal for loop in blueprints. So just to check the setup here, this is the operations we were doing in blueprints. You do for each loop, and maybe you can have some small optimization here if you do like, instead of for each loop, you do for loop maybe, and you can try to pass in length or something, but even that might not speed it up, because then you have to do a get here, but that doesn't matter. Yeah, so we do a for loop, and we just basically get the operand vector, and then we set it in here. Also, I think blueprints, or not blueprints, like loops get some optimizations when you package, so there is like some native visualization stuff. So you might get a speed up, but it's still not going to be even close. It might be like 50% faster or something for the blueprints, but this is like 10,000 times faster, so you can kind of see the actual kind of difference there. You now have different operations that you can do on this mass collection of vectors. You can do multiply by scalar, so this is just like, let's say we take an array and we take xyz and we multiply by, let's say, 5 or something. All of these are going to be extremely fast, that even this print might be inaccurate, because just saving the value and printing it might take longer than, not longer, but it might take like a similar amounts of time to just doing this calculation of 200,000 items. Then we have the normalized array, for example, meaning like we can have vectors and maybe they're like bigger than 1 if you are familiar with unit vectors, and this is just going to normalize it. So this takes a little bit longer than just normal calculation, so we might see actual some difference here, where it's in here like I don't know, 40 microseconds instead of like 20, but in general everything is pretty simple and pretty cheap. This Hadamard multiply is just a simple multiply where you multiply vectors like xyz with another vector xyz, while we had multiply by scalar. This is just like XYZ, you just multiply by one number. So in Hadamard one, what you can have is basically X maybe is multiplied by 2, Y is maybe by 5, and Z by 9 or something. So you can have like different for each. That's kind of the biggest difference. So let's go over some other more interesting stuff here. So for example, we can have something like a get points in frustum. Basically, whatever the camera is seeing, we want to get only those points. So if you have like mass numbers of points, maybe like 10,000 points, if you go in here, we just activated it, so now we only get the points that we see through the camera. And you can find all of them in here if you want, but points, frustum, oh no, get points, sorry. Get points, frustum. Let's find this. So this is basically how it looks like. You just need to get the camera view. So what is the actual view here? And if you break, you can see it has like a bunch of information for the camera. What is location? What is the field of view? What is the width? So you know aspect ratio. So you get all that info from the camera, and you get the points, and then you basically calculate and see if the points are inside of that. And in here we just get the information about who is inside and who is not inside the camera view. That's fine. Let's now go to these compute separation forces. So what this basically means, we have hash and brute. Brute basically means we are going to calculate each point and check each other point to see how far it is and if we need to kind of push it away. And this scales non-linearly. So what that basically means is every time you multiply the amount of points you have to check, it is 4 times more expensive. So if you have 10 points, that means that each point is going to have to be checked 10 times, so for each other point. So that's 10 times 10, that's 100. For 100 points, that's going to be 100 times 100, so 100,000. So we went from oh no, it's going to be 100 by 100, that's going to be 10,000, sorry. So we went from 10 by 10 being hundreds to 100 by 100 being 10,000. So you can see kind of how it scales. If you have like 10,000 points, that's like 10,000 times 10,000. So that might be like a billion or more. So it can get pretty expensive. And then we have this hash, which does some work up front to make it O of n instead of O of n squared. If you are familiar with like the scaling kind of theory there, where this hash value is actually slower than the brute really fast but badly scaled function. It is slower for smaller values. So if you're doing like 50 points and trying to compute separation forces, brute version is going to be faster. But for bigger values like 10,000, the hash function is going to be faster. So you kind of need to pick which one you want. And maybe in the future I could create like a function that doesn't let you pick, but it picks itself or something, because we can just kind of figure out how many points you have and do some calculations there. But that is the general idea. You kind of compute and then, yeah, actually I can just test it here just to show you. So we compute and we have the distance at which points separate, and yeah, when they go outside of that distance they stop separating because yeah, they're far away enough. Then we have get closest actor, so we just calculate the distance. I picked like few actors from the level and just computed which is the closest actor. So then what we can do here, just to kind of check it, static mesh actor 27. So this is this sphere. So from the spheres I selected in level, this one is the closest one, and we can see the distance and which mesh it is. Then we have smooth path. So if I pass in here, this is something that you could trigger per tick, and it takes all of the points and then calculates smoother path for them basically. You have a snap points to ground, and for this one, if you kind of look at their cost, this one might be a bit more expensive than some others, but that is because we have to start using Unreal's functions that do some calculations. So snap points to ground, it needs to ray trace below itself, it needs to check the collision, and then based on the collision it changes the location. So it does some stuff that increases the cost and minimizes how much optimizations we can get from like SIMD calculations, but if we kind of check it, we have distance 2 meters, so this point is above 2 meters, but the others were not, so they snapped. So pretty straightforward, but we can also check it in here. Oh, we cannot do that. Let's do snap points to ground. So basically we have points, we have the trace distance or ray trace, and we have the channel, so what we want to check. And yeah, it's pretty kind of straightforward. Make transforms from arrays. This just kind of shows you the time. So it took, for 200,000 of them, it took, I think it's like 100 and something microseconds. So 1/10 of a millisecond for 200,000 of them. And we can do make transforms from arrays. So what it basically does is it takes location, rotation, scale, and then creates transforms, and then you can pack them basically into a transform and export them. So it kind of does that thing efficiently. Then we have simulate verlet train. So these basically points that are kind of connected together and they simulate. So I have a trigger in here where it kind of starts moving them, and yeah, basically uses gravity and stuff like that. We can actually check this in here. So there is some stuff that you would have to do. Is basically get the position, then we get old position, so where it was before. We have our gravity. So if you have no gravity, it's not going to have the downward pull. So it's going to only have like velocity or like change in position from one frame to the other. Damping, how much it slows down. Delta time, how much basically time is passed. If you're doing this everything tick, it might be like 0.0333 or whatever. For the delta time for like 30 FPS game, but yeah, you can do that. Rest length, so this is basically the distance between them. Solver iteration, so how many solve times it's going to take. So the higher value is going to do more solving, but it's going to cost more. And if you want to lock root, so basically we saw how it fell down and it kind of started like wiggling or like holding onto that one point, so we kind of snapped the root. And we also have the root target, which was this sphere 9. And in here this sphere 9 would be this point. Basically this was the root. Next one we have is move points towards target. So this is pretty self-explanatory. You have a point, that point is a target, and then you have an array of different points that you pull towards the target. Now keep in mind this library and all these functions are just moving the vectors. So the actual update of the points is done. So let's do towards target. So the actual update is done based on the it's something that you have to do manually basically. So we get points and then a for loop, and then you just set actors. Of course, you could do it in a better way. I just did it here and quickly just kind of showcase what's happening, but you kind of have to set it manually. So this also has some cost, but it's kind of hard to avoid Unreal's internal function that is going to do a bunch of stuff when it moves the actor. So this function is better paired with stuff like instance static meshes or stuff like that. Not like setting the actual actors, but you can also do that and kind of just use the plugin to minimize this cost if there is like mass amounts of points that you need to calculate, kind of moving stuff towards to. This can minimize that part, but then all of this cost you'd have to kind of find another way if you are setting the actor basically. But this move points towards target, you just have whatever the target is, list of points. Speed is kind of connected with the delta time, so this like how much. So again, this would be your tick usually. If you're doing it over time, you probably don't want it like instantly. And hit radius, how close the points can basically get, and then trigger that they are basically hit, or they like came close enough to the actor where you're satisfied with the movement basically. Then we have just diffuse grid, so grid of points, and then you have all of these points have values, and then how their values are kind of spreading out. If you are like, I don't know how I'd show this visually, but it's like if you're like using like a blur filter in Photoshop or something, like how it kind of blends the values. And here it shows basically how long that took. So that's kind of the overview of all of these functions. If you ever want to, you can close this. If you ever want to just see whatever this plugin has to offer, you can just do SIMD. And this is basically all of the thing, everything in like SIMD BP here is the functions, and you can see kind of stuff in here. Last thing that we're going to cover is just enabling this, and we're just going to do the mass just the mass activation of all of these functions, and we're going to go to output log. I'm just going to clear it, press play, and let me press play again. And what we're going to do here is type SIMD, SIMD BP here. It's kind of hard to see, but let's actually increase the size here. So what you have in here is basically your SIMD, all of these functions that we talked about, and you also have some information. For example, what type of SIMD was done, or like what type of optimizations, because it's different architectures. Then you have what was the amount, how big was basically the array that this was done on, and then how long it took. So for example, for computation forces for the grid, this is the thing we talked about where it can get pretty expensive. So you can see in here it took 74 milliseconds to do this, and I think normally this would be done, I think this is brute force. Oh no, this is grid, never mind. For brute force, for the same amount of points, I think it took like 250 milliseconds. So this was like 5x faster. And if I like double this, it would take like 4 times more for the brute force, while for this one, I think it should take about the same, maybe like, it might increase a little bit because you do have to go through all of them to hash them, but yeah, you can kind of see all the differences, what was used, count, and some additional information if you want to quickly debug. If you want to do some additional stuff, you can also do Unreal Insights trace and see kind of the cost compared to blueprints or other functions, so you can kind of compare how long it takes. But in here, if you take like some of the cheaper functions, like subdividing, like these numbers are essentially free, basically for large amounts, like 100,000 points. We only took like 50 microseconds, so 120 to 1 millisecond basically. So yeah, that's about it.